Hey, science peeps! Welcome to Geologic Time Part B, where we are going to be talking about geochronology or radiometric dating. Okay, so this is the International Stratigraphic Chart. You will not need to memorize this, God forbid if you do. You will not need to know this for your exam. Okay, this is just something neat that I put in here because it's something that we mention over and over again. We see it in our lecture with paleontology, thanks to Dr. Slattery. We will be mentioning it in stratigraphy and stratigraphic chart. So this chart was made thanks to paleontology, stratigraphy, and later radiometric dating. Radiometric dating is the reason that we are actually able to have the ages for each of these, but it's really because of paleontology and stratigraphy itself that we were able to break it up into what we have today. And this is constantly being updated, just so you know. Like every so many years, it gets updated because we find out something new. So anyway, yes, the part that we are interested in today is this, which is due to absolute dating. Absolute dating is the quantitative form of dating. And there are three major types: layer counting, tephrochronology, and radiometric dating, all three of which we are going to talk about today. So layer counting and tree counting and glacial varves are part of layer counting. So we're going to start with glacial varves. Glacial varves are 2 millimeters to 2 centimeters thick, and these are the deposits in lakes during deglaciation. So deglaciation is when a glacier recedes or kind of like melts away. And so one annual varve is a combination of this dark line and this light line, which means winter and summer. So your winter or dark layer is going to be made up of organic material and clay that filters down through the water during the winter thanks to decay. And your light layer in the summer is due to silt and sand from the melting season that gets deposited into the lake and filters its way through the water slowly. As part of why, if you ever noticed, underwater it kind of looks sparkly. That's silt and sand falling through, as well as, other things like fish scales. So your age is calculated by counting backwards from the present, which basically is going to be the top of the silt layer. And this is reliable up until about 15,000 before the present era. Dendrochronology is the other type of layer counting, and this has to do with tree rings. So tree rings used to be that they would count the rings of a tree after they cut it down. And they will still put trunks of these on display. But today what they do is they will take a core from a living tree, leaving it still living, and then count the rings. So your outermost rings are your youngest, and your innermost rings are your oldest. So it goes backwards. And you're doing the same thing as with glacial varves. The light piece is summer, and your dark pieces are winter. Okay. And again, light pieces are light because, hey, this is when you're getting a lot of water and nutrients. It's in the summer. Your dark pieces are in the winter when you're not getting a lot of nutrients and water, so you're kind of condensing. You'll also see some pretty cool things. You'll see maybe one summer is really narrow. Okay? Really narrow summer ring. That means it didn't get a lot of water or nutrients that year. You can see where maybe it was affected by something that happened around it. Like, for example, maybe industrialization happened and you can see some sort of impact on the tree ring, or you can see if it was close to the nuclear testing sites, or you can see if maybe it was harmed by a storm, which is cool. Oh, dendrochronology is only useful up to 9,000 years ago. Tephrochronology is the volcanic ash layers in drill cores. And this gives an absolute age estimation of sedimentation rate and relative age of sedimentary layers. So for example, let's say this is our ash layer. We know that maybe this eruption was in 1802. And maybe this layer of tephra is from 1952. Okay, so we can basically say this much sedimentation happened between these two eruptions, meaning that maybe there was just a lot of snow that year, and so you had a lot of runoff, or maybe other events occurred, but it helps you say, okay, each one of these is a distinct layer. Here's what deposited when, and here's how long it took for that to happen, which is pretty nice. Okay, and then we get to radiometric dating. So radiometric dating is basically the absolute dating of something using radioactive material. And radioactivity is something that we as a species have been very interested in for some time. Since I guess you could say we first split the atom. It's where we've gotten nuclear energy. It's where we've gotten the nuclear bombs. A lot of things, especially dating. You also have glassware that's radioactive from the 70s, 60s. Basically this really pretty green glass plates and cups and stuff that they're green not because of paint or some sort of coloring. It's green because of uranium. Yeah. Great, right? Anyway, so in 1896 we have the discovery of radioactivity, which paved the way for precise dating of events in the geologic record. And this was done by Henri Becquerel. And then in 1905 we have E. Rutherford estimating the age of uraninite. And about 500 million years based on its helium content, which she did with physical experiments, and it won him the Nobel Prize in 1908. And then in 1950, we have the invention of mass spectrometers by Near, which really enhanced our dating techniques because it allowed us to take really great measurements of things. So, for example, thanks to mass spectrometry, we are able to look at how much argon is in a sample compared to potassium. So there are three types of decay that we're going to talk about. We have alpha particle decay, beta particle decay, and electron capture. Alpha particle decay, an alpha particle is emitted by a neutron, which is 2 protons and 2 neutrons, which is basically 1 helium atom. The mass number is reduced by 4, and the atomic number by 2. With beta particle decay, an electron is removed from a neutron, and it leaves the nucleus. Okay, and this is known as also beta particle emission. And in this case, your neutron will become a proton because it has just lost its electron. In this case, the mass number will remain the same, but its atomic number increases by 1. In electron capture, it's basically the opposite of beta particle decay, where an electron enters the nucleus, mixing with a neutron or a proton forming a neutron. And in this case, again, mass number stays the same, but your atomic number decreases by 1. All right, so we're going to go over this again. Alpha particle decay, also known as alpha emission. Okay, you are going to lose 1 helium atom from your nucleus, which is 2 protons and 2 neutrons, right? 1 helium atom. This will reduce the atomic number by 2 because you've lost 2 protons, and it will reduce the mass by 4 because you've lost 4 parts of your nucleus. Okay. In beta emission, your nucleus is emitting an electron. Okay, so an electron escapes, meaning one of your protons will become a neutron and an electron. Okay. With electron capture, it's the opposite. In this case, an electron decides it's going to enter the nucleus, and so it will mix with a neutron forming a proton. Okay, in this case, you are increasing in atomic number. Sorry, you're decreasing in atomic number because now you're making a neutron. So let me erase this and rewrite this because I just went and confused myself like a dum-dum. Hey. Sorry. Okay, so in this one, you're getting a proton out of it. In this one, you are losing a proton because you're doing an electron plus a proton, which gives you a neutron. There we go, which hopefully you all remember from your chemistry class. All right, so the initial isotope or parent is unstable and so radioactive. Okay, so radioactive is your parent and it is unstable or unst. All right, it will decay and will become a radiogenic isotope, also known as the daughter. And this is stable. Okay, so not all decay pairs have a stable daughter. Some radioactive isotopes as parents will become radioactive isotopes as daughters, and they will continue to decay until they become a radiogenic isotope, which is stable. Right? The pairs that we tend to focus on are a parent-daughter from radioactive to radiogenic. Okay, but for the most part, radioactivity isn't perfect. Through each half-life, an isotope will split in half. And this process is almost infinite because if you don't know, when you split things in half, you don't actually run out of it. You can just keep splitting it in half all the way down to the subatomic level. Fun stuff. And it does start with a 1-to-1 ratio, where you will have one parent to one daughter. And then the parent will split. You'll have 1-to-4 and then 1-to-16 and etc., etc., etc. Okay. But remember, your unstable radioactive parent, at what we're looking at, will become a stable radiogenic daughter. Okay, radioactive to radiogenic. Parent to daughter, stable, unstable to stable. Okay, cool. All right, so like I said, not all elements are stable. Not all elements are unstable. So this line right in here of white is our stable elements, okay? And then we have different types of isotopes. We have aluminum 27, 28, 29, 30, 31, 23, 24, 25, 26. Everything outside of that white line that goes down the middle is an unstable radioactive isotope, okay? Some of these, as we can see, are just a couple of seconds or not even, and other ones can be millions of years. Like that. Boron 14 is around for 16. I can't tell if that's seconds or millions of years. We're going to pretend that says, this is my problem. Here we are, boron 10, 1.6 billion years. Okay, that's something that's useful to us, as long as it turns into something stable versus something unstable. So if it turns into, let's say, lithium-8, lithium-8 is still unstable, and it may turn into helium-6, and then into helium-5, and maybe into helium-4, okay? And we're going to be looking at its stable isotope, its last in the chain, right? So for example, we might look at a chain that ends with a stable isotope, so we would say, okay, well, what came before that? Maybe it's thorium, maybe it's not. If it's thorium, lead, that's what we're going to be looking at. All right, so radiometric dating is the most reliable method for dating rocks. Rocks. Okay? Rocks. Don't say bones. Don't say a book. Well, okay. Carbon-14 dating is the exception to this rule. This is good for dating material that is only about 6,000 years old. But for the most part, rocks. Okay? And not just any rocks. We are looking at igneous rocks and metamorphic rocks. We do not date sedimentary rocks. Not because they're less than us, but because they're made up of multiple parts and it would be impossible to actually date the entire rock. You'd get too many ages. So the rate of decay does not vary for many isotopes, meaning there's very few isotopes that decide, today I'm going to have a half-life of 5 million years. Tomorrow I'm going to decide to have a half-life of 5 hours. that doesn't really happen. You're always going to have a consistent half-life of, let's say, 4.2 billion years. And that's a long time. Okay. The rate of decay has been precisely measured through a radioactive isotope's half-life. Okay. And remember that a half-life is how much time it takes for half of the material to decay. The daughter product is an accumulation at a known rate since the rock was formed, almost like a clock. Right, so the rate of decay from parent to daughter isotope depends on its half-life, or the amount of time that is needed for the parent to decay to the daughter. Okay, so the lifetime of half the radioactive isotope in the system, and the parent is never, ever, ever used up completely. Okay, and the sum of the parent and daughter is always constant. And so we have a chart here where we go parent isotope to daughter isotope based on half-life. So here we have 100% parent. In the next case, we're going to have 50 and 50, which is our 1-to-1 ratio. And then it will be 25, 75, etc. Okay? The only time you have a 1-to-1 ratio is at this point right here after the first half-life. Only time they're equal. But you can always add them together to get how much of the parent you had originally, and they will make one whole. Okay? So this is essentially what the decay series will look like. You have 100% of your parent, you have a half-life, you have 50-50, 2 half-lives, you will have 25-75, okay, and then 12.5 to 87.5, etc. And there is an equation to solve this. You do not need to know it because you are not geologists taking a geochronology class. Aren't you lucky? Yes, we have a lot of math in geochronology. And so this is based on the time required for half of a given quantity of radioactive atoms to decay. So basically, it's an equation to figure out half-life if you do not know the half-life. Okay? Basically, what this turns into is half-life is equal to 0.693 over lambda. So half-lives for radioactive isotopes are like clocks. Okay, they will constantly go at the same time. And they're useful for determining how long a rock has been around. Okay? These radiometric systems are known as decay series because we do have certain ones that are very efficient for this. And they're only useful if it is in a closed system, meaning no new parent can be added and no daughter can escape. This means you kind of have a box with holes if it is an open system. If that helps understanding, which means your daughter can escape and a parent can still come in, versus a closed system being a solid box where no new parent can come in and no new daughter can escape, meaning that your clock can start ticking and you can start seeing, okay, here's how much parent should be in there. And here's how much daughter should be in there. Or based on how much daughter there is, you know roughly how old it is. Okay. Rocks can only be radiometrically dated if all the minerals are formed at the same time. Okay. This is why we use radiometric dating for igneous and metamorphic rocks, because basically the clock will start at all minerals at the same time. Sedimentary rock tends to include particles from many ages since it is made from eroded material. So you'll get ages from all over the place. So when it comes to igneous rocks, the minerals may be floating around in the magma for a little while, but the rock itself will form all at the same time. So it is important to use the proper decay series for the proper job. If you can guess a system is not going to be millions of billions of years old, maybe use a different system than, I don't know, thorium-lead. We have 5 radioactive isotopes that are particularly important to geology. That is rubidium-87, uranium-238, uranium-235, yes, there's more than one, and thorium-232, and potassium-40. Potassium-40 goes to argon-40, and it takes about 1,250 million years old, or 1.25 billion. And then you have samarium, neodymium, uranium, lead, uranium, lead, thorium, lead, rubidium, strontium, and carbon, nitrogen, 14. And all of these will have varying age dates, which is neat. So what is a closed system? Sure, that's all on your minds. So remember that crystal structure we learned about pertaining to minerals? Okay, this is where we would find these isotopes. So we're going to make this our little tetrahedron. Here's our silica, here's our silica, and now we're going to have our big boom boom up here. All right. Basically, as we should know, all atoms are not the same size. Okay. So the crystallization of magma will essentially chemically differentiate parent and daughter isotopes. So a parent mostly prefers to be in the crystal, and the daughter prefers to be in the remaining magma. Daughters tend to be what we call not compatible with a mineral, mostly because it doesn't fit in the socket it's supposed to go into. So that's why we will see our parent within the mineral matrix. Okay. So the parent ends up getting fixed into the crystal as it forms, and once the crystal has cooled enough that it is no longer going to have this switch occurring, the timer starts, and parent will start decaying into daughter, but that daughter can no longer escape, allowing for the daughter to accumulate at a predictable rate. So a system will close or remain closed as long as it's below the Curie point or Curie temperature of a mineral. The Curie temperature is the temperature at which certain magnetic materials undergo a sharp change in their magnetic properties. It is basically also when a mineral is cool enough that it won't undergo chemical changes anymore. Some minerals have a lower Curie temperature than others, some have higher, and it's why only some are good for dating. This means that during metamorphism, that yes, minerals will open if they hit their Curie temperature, releasing their daughter material, which is why you can't accurately date the mineral and why you can't accurately date the formation of the minerals, but you can date when the metamorphism occurred. So let's look at potassium argon. So some minerals crystallize too early in the magma, and so it'll have a high closure temperature, and you don't want that. And some minerals have inherited argon, which you don't want either. So you want basically feldspars and ground mass. Ground mass is like glass. Feldspars are one of the last things to form, which is why it will have pretty much all parent and no daughter. Okay, particularly with potassium and argon. And so what we end up doing here is you're going to get rid of all the other stuff by crushing the rock into small bits and then using something called heavy liquid separation. And I know that doesn't sound like it makes much sense. It's more of it looks at density, and you make the liquid denser or less dense by adding certain chemicals to it, which are extremely bad for you, and you're supposed to wear a gas mask. Just so you know, heavy liquid separation is dangerous for you, but it is a way for you to change the density and so allow for the material you want to maintain their buoyancy and other materials to sink. And this allows you to get the material you actually want, which is cool. So these systems can be used to date the proper age range. Okay, so remember, if you know that your thing isn't going to be billions of years old, maybe don't use thorium lead. So you're going to look at, let's say, rubidium and strontium. Your decay constant is basically 1.4 to e to the negative 11, okay? But your half-life is 4.88, like a billion years, I think? Million years, 4.88 billion years, yes. So your age range is 10 to the 7th to 10 to the 9th, which is in your billions. It's pretty old. And you're going to be looking at felsic, igneous rocks, metamorphic rocks, case spars, micas, and something you all haven't heard before, but it's called glauconite. If we look at potassium argon, This one has a very wide range. It goes from 10 to the 4th to 10 to the 9th. It has a half-life of 1.31 billion years, and it's igneous rocks, metamorphic rocks, and potassium-rich minerals, because it's potassium argon. In this case, we're looking at muscovite, biotite, hornblende, but these can all be easily opened during metamorphism, hence why in any of these, you do not want an altered rock. An altered rock means it's been metamorphosed, maybe, especially if you're looking at the age of an eruption. You also don't want something that's been heavily weathered, because they will essentially turn into mud, and that is not fun, I can guarantee you that. It's not cool trying to cut your sample and have it just go, I have decided to be mud today. And you're like, great. This is what happens when geophysicists decide to go in the field, and they're like, oh yeah, we'll bring back samples for you. We can totally do that. Even though there's no geochemists with us in the field, and somehow we'll get this done. Get it back. You have mud samples. Woo. In case you can't tell, this has happened. And it was very frustrating. So how do we figure out ages? Yeah, sure. We put it through the mass spectrometer and it comes out with all these numbers. Wonderful. What do we do with it? Well, what we do is we use the age equation. Again, you will not have to do this. You will not have to make an isochron. You guys are all very lucky that you don't have to do this. Unless you really like it, in which case take a geochronology class. You'll have a blast. So we are using one from potassium argon dating, where we have potassium argon down here, and then argon over here. And we make something called an isochron, which is this graph. And this graph, the slope will give us the age, basically. So what you do is where the line intercepts, you have your initial argon, which is the B. Okay, and then the slope is determined by subtracting the highest and lowest value of potassium argon and then dividing them. And this is where you plug into the age equation, which gives you the age of your sample. Remember, slope plus 1, y equals mx plus b, essentially what you're looking at. Okay, so what about dating rocks? Well, I suggest the first thing you do is you go and get them a rose, and you tell them, I think you're beautiful, and I will take you out on a date. And then, while they're distracted by their dinner, you smash them up into itty-bitty pieces. And then you use, let's say for potassium argon dating, you go and put them through a separation cycle with heavy liquids. And then you stuff them into this little container that is essentially tinfoil. And you heat them up really hot, and you get them to give off their gas. And then you use that gas to figure out how old they are. Yes, it's exactly what you do. Maybe without the rose or the dinner, but that's essentially what you do. So radiometric dating methods have been used to determine the age of the oldest rocks so far that we found on Earth. So we have found 3.5 billion year old rocks pretty much on all continents. And so far, the oldest rock itself is about 4.28 billion years old, and that's located in Quebec, Canada. Although we have found a zircon, because remember, zircons, oh wait, I didn't tell you this. Zircons don't melt. And this is what we use for the uranium series, uranium, thorium. Zircons are cool. They do not melt. Once they form, they just form new layers. And so they kind of make rings of minerals on themselves, and you can date each one of these layers to figure out how old each layer is. So it allows you to figure out how old, let's say, a volcanic system is, because maybe the first eruption or the first magma intrusion into a digerous sill below the volcano itself is this, and then we have the next one, and the next one, and the next one, and the next one, and it is pretty cool. So someone has dated a zircon that was actually closer to almost 4.6 billion years old, which means it's essentially been around since the Earth was molten. We have a 3.7 to 3.8 billion year old rock in Western Greenland, a 3.5 to 3.7 billion year old rock in Minnesota River Valley, Northern Michigan, 3.4 to 3.5 billion year old in South Africa, and another 3.4 to 3.6 billion years old rock in Western Australia. The moon has been dated as well, and they have found rocks to be closer to 4.6 billion years old. So it's pretty cool. We can definitely say that the Earth is about 4.6 billion years old because of this, which is cool. So radiocarbon dating uses carbon-14 to date recent events because the half-life is only about 5,730 years. So what is this even useful for? It's for things in our recent historic past, such as recent geologic history, bones, fossilized plants, okay, as long as it's within a certain age range. Okay, remember, half-life, 5,730 years. This allows us to date fossils, which is cool because all of us have carbon in us. All right, so we are considered an open system while we are alive. And once we die, they can figure out how long ago we were alive based on how much carbon is left in our system. Because once we die, the carbon starts essentially disappearing. It turns into nitrogen and then, well. So they look at how much carbon is remaining using carbon-14 dating, which is pretty cool. So this appears in French. Sorry, shouldn't be too hard to figure out. Carbon-14 uranium series. So for the most part, these are color-coded, but not really, because for whatever reason, like over here you have rubidium, strontium, uranium, lead, and neodymium, samarium. But for whatever reason, they don't, I don't know why this isn't erasing, they don't have the uranium lead one. They have it in series uranium, which stops about here, which doesn't make much sense. Anyway, potassium argon is perfect. Potassium argon does have the largest range, which is pretty cool. It goes from a little bit before 10 to the 4th to a little bit past 10 to the 9th, which is pretty neat. Carbon-14 dating has an application of 100,000 years and 40,000 years. Okay, so A is 1,000 years, GA is billions of years, or hundreds of years, thousands, hundreds, 100 years ago and 40,000 years ago is essentially what it is, because A equals years, hence the A. KA is thousands of years, MA is millions of years. So the geologic time scale is updated constantly. And this is because we're constantly finding new stuff, new information that helps split these eras further. So for example, a few years ago, the Cenozoic was divided into the Tertiary and Quaternary. Today, the Tertiary is the Paleogene and Neogene. Just like the Carboniferous was broken down to the Pennsylvanian and Mississippian, which has to do with glacial ages, and their names actually came from how far south the glaciers came. So for example, the Pennsylvanian came down through Pennsylvania, the Mississippian went all the way down to Mississippi. And that is our lecture on geochronology. If you have any questions, please make sure to post them on Canvas. If you are trying to fill out your study guide like you should be, and you have trouble figuring out all the answers thanks to the slides, please, again, post your question on Canvas. Have a great day!